Okay, so let's look at another major component of data preprocessing, and this would be data reduction. Okay, so the agenda here, we're going to discuss data reduction. So again, here, when we talk about data reduction, we're talking about how to reduce probably the volume of the data set, or also reducing the features, for example. Okay, so discuss why we perform, what is data reduction, why we perform data reduction, and look at some of these three techniques of data reduction. So when you talk about dimensionality here, we're referring to here to variables or attributes, or sometimes we call these features. These are your columns, right? The columns that have the features, right? So if you have x1, x2, x3, okay, these are what we call features, okay, or variables. All right, so now let's look at what is data reduction then. So data reduction is just a process that reduces the volume of the original data, right? And we want to represent it in a much smaller volume, okay? So why do we perform data reduction? Well, when we have smaller volume of a data set, or probably a compact data set, right? Then you simplify the process. And when you simplify the process, it becomes computationally efficient, to apply probably a complex or sophisticated algorithm, okay? And again, here, we can see here, so we want to just get a representation of the data, okay? What that means, we have a much smaller volume, right? Okay, and it's much easier to do some data analysis on that, okay? Another thing I want to talk about here, so for example here, if you wanted to, let's say we wanted to predict a student's GPA, right? Clearly there are some attributes that will be irrelevant, all right? We want to select only those attributes that are relevant, right? So clearly here, your social security number will not probably, have an influence on your GPA, okay? Probably features, you want to include features like, how much time you spend on study, number, if you finish your assignment or not, and things like that, okay? So another reason here for performing data reduction, clearly here reduces the time and storage space required, right? So again, here we're talking about some element called multi-collinearity. So we have multi-collinearity, okay? So this is just a term you encounter as a data scientist, collinear, okay? Multi-collinearity, I'll just abbreviate that, okay? So when you remove that, you kind of just improve the interpretation of your parameters, right? It makes it easier for machine model, right? So multi-collinearity here simply means, when you have high correlation between two variables, right? So maybe we have x1 here and x2. Okay, so when they are highly correlated, right? What that means, they are linearly, you can linearly predict, one variable from the other, with a bit of accuracy, okay? Sometimes we call these predictor variables or independent variables, okay? So we want to remove that, and that's one other reason we perform data reduction, okay? Again, I would say here, it becomes easier to visualize your data, okay? You reduce that to probably low dimensions like 2D or 3D. So let's see here, if you had almost 1,000 attributes, right? This is a whole lot of data, right? You can represent this probably in a plot, right? These are 1,000 dimensions. Remember, we want to reduce those dimensions. So probably might be much easier to represent that maybe in a 2D or 3D when we reduce it to maybe 10 features or 10 dimensions, right? And lastly here, we want to, another reason is to, something called the curse of dimensionality, right? We're going to look at this in a minute. Dimensionality, right? The curse of dimensionality, we want to remove that. Okay, now that we know what data reduction is and why we perform data reduction, now let's look at this curse of dimensionality, right? As I mentioned, in any algorithm, it will be very challenging to kind of analyze 1,000 dimensions, right? And the general idea here is that the more dimension you work with, the less effective, right, your computational or statistical techniques will become. All right. So it behooves you to sort of reduce your features to make it much easier, more manageable, right? So let's say if you want to predict if somebody has cancer or not, right? Not all attributes will contribute to that. So sometimes you want to remove the irrelevant attributes like telephone number, for example. Probably want to just include the historical, the history of that patient, right? In terms of family, history, right? You want to see, the weight, probably age, if predisposed to diabetic history, and so on and so forth, sugar levels. Those are some of the relevant attributes we want to include. So again here, so the density and distance between points for clustering here, especially if you're using cosine similarity, okay, that means if you have 1,000 dimensions, there will be so much sparsity in your data, right? And then the more you have so much distance in between here, then that distance becomes less meaningful. Okay, so this is what we call the curse of dimensionality. I'll just give you an analogy in a short while. Okay, but the solution here, once we remove that, it kind of helps to eliminate relevant features and reduce the noise, as I've already given an example, right? And then, of course, the less attributes you have and more relevant you have, kind of reduce the time and space required in analyzing in data mining, right? And you can see here, when it comes to visualization, it becomes easier. So let's say if you have 100 attributes, right? So let's say if you have 100 attributes. So if you have to visualize this, that means you'll end up having maybe 100 scatter plots, right? So that'll be just it'll be very time consuming and very computationally expensive, right? So as opposed to maybe having 8 attributes, right? You can easily visualize that, having 8 scatter plots to visualize that, right? And you can now, from this, you can perform additional techniques like correlation analysis, chi-square, and so on and so forth. Okay. But now let's look at curse of dimensionality. Again, this graph just shows you. So when the number of features here is very large relative to the number of observations, so number of features here, okay, it's large based on the number of observation in your data set. Certain algorithms may struggle to train the effectiveness of your model, right? Okay, so this is the curse of dimensionality, all right? Okay, and you can see here in some literature, you find that as the dimensionality of the feature space increases, the number of configurations can grow exponentially, and thus the number of configuration covered by an observation decreases. Okay, let's look at an analogy here. So I got this very good analogy from Quora, right? So let's say you have a straight line, right, which is 100 yards long, right? And probably you drop a penny, right? So if you want to find it, right, it will be too hard, right? You can just walk back and, within a minute or two, right, you should be able to find that penny, right? However, if you probably have an area that is a square of 100 yards, okay, 100 square yards is probably almost like 2 football fields stuck together, right? And then you drop a penny, right? How much time do you think that this will take you, right? Probably will take you days, okay? Maybe may take you weeks and all that, okay? So, and then lastly here, now think about a cube of 100 yards across, right? That's almost like searching through a 30-story building, okay? That's the size of a football stadium, building the size of a football stadium, right? Now, trying to find a penny in this kind of setup, that would be just crazy, right? So this is the curse of dimensionality. The more features you have, the more sparsity in your data, and the more challenging it becomes, right? It becomes a lot harder when you're dealing with more dimensions. And really, this is the reason why we perform data reduction, all right? just to make it easier for complex algorithms to sort of analyze our representation of our data. Okay. All right. So now let's look at some of the techniques that we can use. We have principal component analysis and attribute subsets collection, selection. All right. So let's begin with, I want to spend some time here, talk about PCA. So most times it's abbreviated as PCA. And this is a dimensionality reduction technique, right? Often used to reduce the dimensions of large data sets. So we use PCA to reduce the dimension of large data sets, okay? How do we do that? We transform variables. We transform these very large variables into, so we transform these large variables into small variables. Okay, that's what PCA does. Okay, all right. And these small variables, when they become smaller, that means we want to make sure it still contains much of the information from the large data set. Okay. Now, PCA was first introduced by some mathematician or statistician. I think, for those who come from statistics background, you might have come across this formula, Pearson square. The guy was called Carl Pearson. So he's the one who earlier on really saw the need of using PCA, especially when you're dealing with high dimensional data. Okay. Again, another thing to keep in mind here is that PCA also has become one of the most widely used multivariate statistical technique, right? In fact, it's the backbone of modern data analysis, right? And in fact, it's the de facto and supervised learning. As a data scientist, you'll be using a lot of PCA for unsupervised, okay, unsupervised sort of projects. It's called unsupervised learning, right? Where you just given a sample or given a large data set, right, of unlabeled data set, you can apply PCA to sort of reduce the dimensions, right? And probably we're gonna look at what this process involves to create new components, right? Okay. Again, PCA, we can use it to visualize data. So you can imagine we had 100 attributes. You can actually reduce those attributes probably and just collect or identify only 5 or 10 attributes that actually carry much of the information from your data set. And it's easier to visualize that. Okay. So, and one of the applications of PCA is found its application in pattern recognition, signal processing, and most importantly, in statistics, you might have come across something called FA, factor analysis. Okay, very popular there. If you're going to carry out some research, then you'll come across this. It's in the broad umbrella of factor analysis. Okay, so really here, when we talk about PCA, the goal here is to identify patterns in data. Okay, so if anything, we want to find out the correlation between variables. Okay, so let's look at an image here. So we have an image here. I found this from the net. So here you can see a PCA technique can be used to identify a correlation between data points, such that there's a correlation. We want to find out, is there a correlation between the consumption of frozen food, frozen fish here, and crisp breads in the Nordic countries? Okay, so that's PCA, right? So again here, why do we consider PCA? Question will be, why do we consider PCA as a reduction technique, right? One of the characteristics is that because of if we have a strong correlation between variables, if there's a strong correlation between variables, let's say x1 or x2, or x3 and x1 and so on, the goal here is to reduce the dimensionality, right? So that's why we actually even call it dimensionality reduction technique. So given some attributes, maybe x1 to xn, we want to determine, right, do we have any strong correlation between variables, right? If so, then the goal here is to try and reduce those dimensions, right? So that at least we have just a summary, or we have some smaller attributes for that. Okay, so in a nutshell here, just to summarize this, slide, PCA is all about finding the direction of the maximum variance in high dimensional data, right? You want to project that into a smaller dimensional subspace, okay? So this slide just gives us, this is a very tricky, involves a lot of technical jargons, but I'll try and summarize as much as possible. Those who will have much more interest, you can read more about this, or you can take an advanced class where you can, probably revisit much of the process, but I'll try and summarize this as much as possible. So the first step in PCA, first of all, you standardize the variables, right? What that means, given your continuous variables, right, you subtract the mean, and by dividing it with the standard deviation for each of the variable, each value with the variable, and that we use this formula here. Okay. Once you do that, the next thing is to compute. You want to compute the covariance matrix, okay, to identify the correlation. In fact, we generate that table. Okay. In fact, that table just contains the correlations, right? So to understand, in fact, when you identify the correlation, in other words, you want to understand how the variables in the input data vary with the mean, with respect to the mean, with respect to each other. Okay. So essentially, you're asking yourself, are there any relationship in these variables? Okay. If there are some variables that are highly correlated, okay, what that means, it contains redundant information. So we need to remove some of those variables. Okay. So again, you can see here. This is a formula for covariance. So the principal diagonal here, most times this is just the variance, right? And you'll see that, a covariance matrix. So when you, if you know a bit about covariance, so let's say here we have H and U. So the covariance with itself here is the same as saying the variance of H. Okay, that's just the way it is. Okay. All right. Now, so how do we interpret this? Okay, so in fact here, if the covariance value here is positive, that means when we have two variables, right, H and U, so if they increase or decrease together, then that's when we say it's positively correlated, right? Right. But when it's negative, we say one increase in one decreases, the other value decreases inversely, right? Or rather decreases, we say it's inversely correlated, right? And you can see here, the covariance matrix is nothing more than just a table. Okay, the covariance matrix is just nothing more than a table between all the possible pairs of variables. Okay. Then thirdly here, we compute what we call the eigenvectors or eigen and eigenvalues, right, with the covariance matrix. Okay, so that you can identify the principal components. All right, so here eigen just comes from the German word that means very on, yeah, like very on. Okay, so the eigenvectors and eigenvalues are just a linear algebra concepts that we need to compute from the covariance matrix, right, in order to determine the principal components, right? So when we talk about principal components are just, so let me just write here. So principal components here are basically just new variables, okay? So these are just new variables that are constructed from a linear combination, right, of the initial variables, okay? So just keep that in mind. So the idea here is, let's say if we had 10 dimensions, right? Let's say we had 10 dimensions, okay? So what that means, you can create 10 principal components, PC. Okay. But again, here, PC will try to just put as much information in the first component, and then the maximum remaining information will put it on the second, and so on and so forth. But here, let me just use a rubber here, eraser. If I could remove this. So this is what I mean. So let's say we had, so pen here, just give me a minute, pen. So here, we're given 10 dimensions, right? So the goal here is to try as much as possible to retain as much information to the first component. So this will be a first PC, this is a new component, then PC1, and then PC2, PC3. So you can see here, the first PC1 out of this 10 dimension retains probably 42%. The next one retains maybe 18%. So cumulatively here, the goal is to try as, load more information onto the first 2 or 3 components. Okay, this is the goal here. All right, and then the next thing is to create a feature vector to decide which principal component to keep. So once you have that, you create a feature vector. Okay, again, you once you create the feature vector, you want to determine what to keep and what to discard, the one which is of lesser significance, right? And again, you just order that and pick the one with the greater eigenvalue. Okay, and then lastly here, you just recast the data along the principal component axis. Okay, so and that's it. So that's just in summary the PCA process, but it's much more than that. It's very detailed and there'll be a lot of calculations here and there, but just keep that in mind. So that's PCA. Okay. All right. So let's move on. That's how it looks like, so given this, what do you think, right? So this is just an animation, right? You can see the goal here is to align this line probably towards these purple lines here. And then you can see this red dotted lines. So this is the goal here. We want to align as much as possible all these data points to align into that straight line and create new components. Okay. Now, PCA is without, weaknesses. Actually, one of the main weaknesses is tends to be highly affected by outliers in the data. Okay, right. Since it relies a lot on a linear relationship between feature elements, so it's very unclear, what kind of relationships exist before you start. Okay, that's just one of the weaknesses, and that's PCA. All right, so another technique here we want to talk about here is attribute subset selection. Okay, so let's look at that. So here the goal is to try and reduce the data size, right? So we want to reduce the data size and also want to remove irrelevant set of attributes, right? So let's say here, if you want to classify, like I said, if you want to classify and and see, what patients have cancer, which patient don't have cancer, right? Things like mobile number is irrelevant, right? So want to include things like age, maybe weight. And most times you want to also include probably domain expert can help with choosing the attributes. Okay. So again, that's it. The goal here is to select a minimum set of attributes, right? That will result in a probability distribution that retains as much information as possible, right? So there are 2 ways of doing this. Again, we have forward selection and backward selection, right? Forward selection, that means we start, sometimes we call it with no predictors, backward selection with all predictors, right? So we will look at it individually, but just quickly to mention here. So when we look at forward selection, it's just an iterative method where we start with no features in the model, right? So let's say we have 10 features. So we start with an empty set. Okay, so we start with an empty set, right? And then it's iterative. So each iteration, we keep adding a feature. So like maybe we have X1 here up to X10. So we have 10 features, right? So each time we add a feature that best improves our model, so we keep adding until there's no improvement in performance of our model. And then with backward selection, right, we start with all features, right? All features. So in fact here, so inside here, we'll have our X1 all the way to X10. So here, this is a full model, right? And then here we want to try just to delete. We want to remove each time we want to remove, okay, all those variables or features that are least significant to our model, or rather which does not improve the performance of our model. We repeat this until there's no improvement observed on the removal of the features. Okay, let's look at each of these. So with forward selection, we start with a null model, right? Null model. So it's just like a set. So in this basket, we have a basket here of features. So assume this is our model, right? So by the way, predictors is just another term for independent variables. So predictors, right? So predictors, we can also refer to this as independent variables, IV, or features, okay? Features, okay? All right. So most times, let's say, for example, you're using a linear regression model. So basically here, you want to search through all these variables individually. So we have 1, 2, 3, 4, 5. So each time you have to do 5 linear regression, right? And you want to perform the 5 linear regression and then choose one variable that has, the best, or rather the one that has the lowest residual sum of squares. You pick that, and that will be you retain that in the next iteration, right? So you keep on repeating that, do another linear regression with the combination of x2 and find that one that has the least residual sum of squares, okay? So you keep doing that each time until, there's some rule that is satisfied, right? So, and statistically speaking, most times the criteria we use probably is F statistics or p-value, okay, or p-value. So each time you add a variable here, okay, you're measuring it against some criteria, statistical criteria like F stats or p-value, right? The one that is least significant, you remove it or you leave it. The one that is significant, you retain it in your model. So that's forward selection, right? Now we go to a backward selection. So backward selection, we start with the full model, right? Our basket is empty here. So each time we remove a variable with the largest p-value, okay? So what that means, this variable is the one that has the least statistically significant, okay? So what happens here? So incidentally here, x4 is least significant. So we remove it from our model. So our model now remains with x1, x2, x3, and x5, right? So we iterate that again, okay? We run our linear regression model and we find again, we continue, that will be p-1, and we continue until, we satisfy some threshold, until there is no variable that has a significant p-value, okay, defined by some significant threshold, for example, okay? So as I said here, most times we use the F ratio, okay, just to keep that as your criteria, okay? It's not unusual to combine both the forward and backward selection, right? You can combine both the forward and backward selection, okay? And we just follow through the procedure, right? We want to select both attributes, the best attributes, and remove the worst among the remaining attributes, okay? All right. Another thing I just want to mention here is that, again, so when do you use forward or backward selection, right? So I think it's important. I'll highly recommend, or rather, if you read, you'll find that if you have a very large candidate, a large set of candidate predictors, and you wish to probably extract a few, okay? And assuming you're actually on a fishing expedition, then generally you just want to use the forward selection, right? And on the other hand, right, if you're just fine-tuning or you're just interested in some existing selection of variables, right, where you just want a modest size, set of potential variables, then, and you want to just eliminate a few, then the best approach is to go with backward, okay? But Again, here, just like fishing, you have to be very careful. Don't cast your net too wide, okay? Because sometimes you can select attributes that are, probably not related to your dependent variable, okay? All right, that's it. So now let's look at numerosity reduction. So numerosity reduction here, we want to reduce the volume, okay, of our data set, right? The data volume is reduced by choosing an alternative, right? Maybe a smaller form of data representation. So two methods here, we have parametric and non-parametric, right? Parametric here, we'll look at regression. Non-parametric, we'll look at histogram, sampling, and clustering. So again, here we look at parametric. When we say parametric, we're talking about the parameters, the data points, right? So here is a linear regression, right? We could actually, given some data points, maybe 100 data points, we can fit a line that best describes our data set, right? Just by fitting maybe, two data points here. So we have maybe this one and our C here, right? And probably this would just be enough. So with just these 2 points, we can, W and C, we can actually discard the data, because we have a line that best models our, data set, okay? Although not very elegant, but again, it's an alternative to reduce the volume of your data, right? So that's why we use that. Again, you also come across something called log linear, right? So we have linear and then we have log linear models, right? So log linear here is just an extension of linear regression. And again, these models can approximate discrete, multidimensional probability distribution. So this just allows you to start projecting high dimensional data, probably I think up to 10D. So yeah, so that's just it for now. When we look at histogram, histogram just use binning. We've already looked at binning, but binning are just like buckets. Given this data, we have probably how many? Let's say maybe 100 data points, right? Okay, so we can use histogram to sort of summarize all this data into just a few bins or buckets, right? And this is a very famous form for data reduction, by the way. So given this, we can see there are 2 methods. We can partition the data. We can use what we call equal width, or we can do equal frequency, right? Equal width, equal frequency. Equal width here, like this example, we just partition to 10 equal size, so 1 to 10, 11 to 20, 21 to 30. And then we can say from 1 to 10, we have all these data points, so we have up to what, maybe 16 here. So all these data points that fall between that is represented here. Same with here, 11 to 20, we have probably 25, then 21 to 30, we have a total of maybe 15 data points. So with only 3 buckets, we're able to summarize all this, okay? Only 3 data points on the x-axis and 3 data points on the y-axis. We're able to summarize all these 100 probably data points. So that just makes it very versatile. All right, very effective. And this actually is very effective in approximating, both sparse data. So very good in approximating sparse data and dense data, especially those which are skewed. Okay. So much for that. The other one is non-parametric. We're gonna use sampling. So sampling here is just a statistical technique, right? Which a group of observation are extracted from a large population. We're gonna look at probably 4 different types of doing that. In fact, researchers here choose simple random sampling. Simple random sampling here. It's a very popular technique, just to make generalization about a population, right? And one of the advantages, or some of the advantages of this is because it's simple, right? It's simple, okay? And, there's a lack of bias, okay? Okay. But of course, one of the advantages, some of the advantages just is costly and time consuming, right? So let's look at the first one, okay? So simple random sampling without replacement. All right. So I have this figure with me here. So let's say given these data points, 10 data points, right? So what happens here? So you randomly take a sample, right? So we data point there. Let's say we have 10 data points. We pick 5, and we again we'll pick 7, and we pick 10, and we pick 1. Let's say we wanted to just randomly sample 4 data points, right? So what remains in our basket? Okay, that'll be 10 minus 4. Okay, and that's a simple random sampling without replacement, right? So again here, each data point has an equal chance to be sampled. Simple as that. Okay. On the other hand, we have simple random with replacement. Again here, similar. We have 10 data points. So you you pick a sample, right, and return it. You pick another one, return it. You pick another one, return it, and all that. So you can see by the time we sample 4, randomly sample 4 with the replacement, you can see what's happening here. Okay, there's a high chance that we can repeat, a chosen sample. Okay, so we can actually repeat a chosen sample. Okay, there's no guarantee, in some cases, we can end up picking all these as 5. So again, here in the real world, this might not be a very common approach. Okay. All right. So that's that. Let's move on to cluster sampling. So cluster sampling here is just a method where a researcher would create multiple clusters, of people, maybe from a population that's indicative of their probably characteristics. And each of those characteristics have an equal chance of being part of a sample. Okay. So for example, here, let's say you wanted to, find clusters based on the geographical location, right? Let's say we wanted to find people maybe in the Midwest, in the East Coast, maybe this is the US population, right? So you want to find people from the East Coast, right? West Coast, South, and Midwest, right? So we create these clusters, right? And then from these clusters, we find the people represented in these clusters, right? Then we take samples from this cluster. Then from this sample, we can identify whatever feature we want to use. And then once we have that, we can now apply these techniques. That's cluster sampling, as simple as that. Okay. All right. And then lastly here, we can look at stratified sampling. Okay. So first of all, what do you notice here? What type of data is this? We already looked at it. So remember, we have ordinal, right? We have nominal data type, ratio, and interval. Okay, ratio and interval. So just pause for a second and figure out what type of data is this. So if you guessed it, there's some order here. So this is ordinal data, right? So ordinal data, you can see here we have a cluster of youth, middle age, senior, and so on and so forth. Okay. So how does stratified sample work, right? You can see here we create stratus, right? So what we do here is we divide it into stratus. And this strata here, we have strata for youth, middle age, right? Senior, and so on and so forth. Okay. Now, here is a good question. Now, what happens here if we did not divide it into stratas? Let's say we wanted just to perform probably, let's see. So if you wanted to, probably perform simple random sampling on the entire data set, what will happen? Okay, so that's a good question. That's a good question. You can pause and ask that question. And what do you think would happen? Well, So there's a high chance that, we might end up missing some of the data. If you just apply simple random sampling on the entire data set, we might end up just be choosing, youth. We might be missing middle age and senior. Okay. And that's why stratified sampling is very important, because you'll be taking a sample from the youth, sample from middle age, a sample from senior, and then you apply this one, simple random sampling. Okay. So, and then this is very useful when your data is actually skewed. So there's a good chance that you can better approximate your data using stratified sampling. Very important, especially when you have a large data set. All right, moving on. Lastly, here we have data compression. It's another technique where we transform. It's a transformation, right? We apply this transformation to obtain maybe a reduced or compressed representation of the original data. This is very common with video, audio, and probably streams, right? In fact, here one of the most popular is string compression and audio video. I think I'll talk a little bit about that. But one thing to keep in mind here, we have two types, lossless and we have lossy. Okay, when you talk about data compression, always remember this, lossless and lossy. Okay, when you talk about lossless, right, what that means, after we compress the data from the original data, right, the quality of the data remains the same, meaning that we're able to extract the compressed data back to its original form, right? But with the lossy compression, we're losing some information from the original data. Okay, think of also YouTube, right? Think of YouTube. Most of the video platforms, use lossy. And most times you'll see 1080 HP, 1080p. We have 720, 320. So the lower you go down, you can see that, you lose some quality, because we're using pixels. So you're losing some features, whether it's not sharp enough, the audio clarity is not good enough, and so on and so forth. Okay. So, and then of course, string compression, I think this is one of the best, algorithm that uses lossy. So we have, you can look at an example here, zlib. It's a data compression software, kind of just, if you ever used a data compression like gzip, kind of just combines the Huffman coding, very popular. We also have this broadly, it's a lossless data compression developed by Google. Okay, and also it just uses some lossless compression algorithm like Huffman coding, and very, very popular, compressing HTTP content. Okay, so compressing HTTP content. Okay. Yeah. So that's it as far as data compression is concerned, and this visual just summarizes that. So as you can see here, we have our original data, compress the data. The data, we extract the data back to its original data. We call that lossless. But if we kind of just extract an approximation of that data, we call this lossy. Okay. So, so with that, what's the story so far? We've talked about data cleaning. We've looked at, what is missing data, what is noisy data, how to handle missing data, how to handle noisy data. We also talked about data integration, right? Why we need to find redundancies, right? And we looked at different techniques like correlation, covariance, right? For nominal and numeric data, when to use for that. And again, here we talked about correlation is not causation. Remember, there's always probably a third factor here that's causing that. Remember when we look at that example of hospitals and thefts, right? Car thefts, right? Probably is, probably a third factor, like, population that's causing that. Okay. And in this video, we've looked at data reduction techniques like PCA, attribute selection, forward and backward selection, very important. Okay. Numerosity, looked at regression and parametric, like histogram, sampling, strata, sampling with replacements, and so on and so forth. Data compression. I've looked at the difference between lossy and lossless, and we've seen how most audio and video uses lossy, and most string compression use lossless, right? If you've ever compressed your data using any file software, most times you use lossless. All right, and that's the end of our lecture for now. Thank you.